Okay students, welcome to Darasa Online. I'm Cyprian Mgina, a physics teacher. Today we are going to study physics to the topic of electronics. We shall be looking to the subtopic of an operational amplifier. Basically, we'll be looking on identification of amplifications of an operational amplifiers. First of all, students, we need to know basically what's an operational amplifier. An operational amplifier is an electrical device basically designed for an amplification of AC and DC voltages. An operational amplifier device have got a very high input impedance of about 2 mega ohm with the low output resistance or impedance of an order of about 200 ohms. And this, for that particular case, it is a device which have got a very big voltage gain to a magnitude of about 10 power 5. A voltage gain, that is the ratio of the output voltage over the input voltage. This electrical device has been composed by several resistors, transistors, and capacitors, and had just been developed in a complex way, and that's why we are having what we call an integrated circuit. An integrated circuit in such a way that it can be able to make or be able to perform all over that particular functioning, or to work as an operational amplifier to amplify an alternating current or an alternating voltage to a level of which might be needed for any particular circuitry use. So really we are defining an operational amplifier as a device which can be able to amplify an AC and DC signal. And for that particular case, we'll just be able to find that, as I've already said, that it's just being composed by several resistors, capacitors, and the transistors in a complex way, and that's why it forms what we call an integrated circuit, IC. But we will be able to find that for that particular case, this particular operational amplifier now can just be used for various purposes. As I've already said, that for an amplification of an AC and DC signals. So for that particular case, it can be used, let's say, for signal conditioning, for frequency, for filtering of various frequencies. An operational amplifier can also be used for some particular operation, mathematical operation, like addition, subtraction, differentiation, and the integration. That is all how an operational amplifier can just be used. And the basic operational amplifier have got some 2 inputs and 1 output. Have got 2 inputs and 1 output. The 2 inputs normally are the terminals where we can be able to have our input signals inside it. And the input signal is always direct proportional to the supplied voltage. But we are only having only 1 output, which is real, as we shall be able to see later. That's where we can be able to get what our amplified signal through that particular output terminal with respect to the earth or to the ground. That's about the basic or the definition or a simple structure of an operational amplifier. And the symbol of an operational amplifier. The symbol of an operational amplifier. It is that particular symbol. So we are having 2 inputs, an inverting input and a non-inverting input, and we are having this as the output terminal. So we are having these two input terminal, and that's the output terminal. And the operational amplifier for that particular case can just be connected in a circuit such that it can be able to work as an inverting amplifier or a non-inverting amplifier, depending upon where the two of the 2 inputs be connected in the circuit. Let us go and look at a practical operational amplifier. A practical operational amplifier actually is a simple integrated circuit chip with an 8 pins which can just be connected to the circuitry the way it can just be designed for it to operate. And that particular 8-pin integrated circuit chip of an operational amplifier could just be like this one here. Could just be like this one here. So we are having some eight legs. Could be having leg number 1, number 2, number 3, number 4, number 5, number 6, number 7, and number 8. Now, leg number 1 and number 5. Number 1 and number 5, these are offset null. That is leg 1 and 5. Those are the legs which are normally connected to the circuit to preempt or whatever all signal prevailing within the operational amplifier chip. So we can be able to offset it and put it to a 0 so that it can be now used afresh. But leg number 2, this is an inverting terminal to our operational amplifier. So we could be having our operational amplifier like this. So this is an inverting terminal, and number 3, that is a non-inverting terminal. Number 4, number 2, this is an inverting terminal. Number 3, it is a non-inverting terminal. Number 6 is an output terminal. Number 6, this is an output terminal. And number 4 and number 7, this is for the supply voltage. Leg number 8 is just left hanging and can just be used for any particular use. Okay, so students, let us go now look for the basic characteristics of an operational amplifier. There are 3 basic characteristics. There are 3 basic characteristics of an operational amplifier. The first one, we are saying that any operational amplifier should have a very high input resistance. Very high input resistance. Input resistance to the order of about 2 mega ohm. So what does it mean? It means that all of the signal which is really coming to the input side, as long as the inside resistance is really very high, then it will be able to prevent that all of the current which is just coming there, just a very small bias current can only be allowed to get in, but most of the current will be allowed to go to the output terminal because of the very big input resistance. But the output resistance, the input resistance, we are talking about the way how the input terminal are just connected, let's say, to the earth. But whenever I talk about the output resistance is small. So it's going to have a low output resistance. So it's got a very low output resistance of the order of about 100 or 200 ohm. So it means that whatever a signal is being delivered to the output, most of it will be, all of the output signal will be delivered to the preceding circuit part of the to the preceding circuit part in whatever the operational amplifier will just be connected. And the third property is that the operational amplifier normally have got a very high voltage gain. Have got a very high voltage gain. It means that the ratio of the output voltage to the input voltage is really very high, of the order of about 10 power 5. So that is, these are the three basic properties of an operational amplifier. Okay, now let us see how an operational amplifier works. Operational amplifier can be able to work in either of the two parts. It can be able to work as a non-inverting amplifier or an inverting amplifier. Let us look the first one as an inverting amplifier. As an inverting amplifier. In an inverting amplifier, we are having our operational amplifier be connected in this way. That the inverting terminal is the one which is connected to the earth. The inverting terminal is that is where we are going to have our input. So our input signal is to the inverting terminal, and the non-inverting terminal is the one which is going to be earthed. And the output terminal, that is where we're going to get an output. We're going to get an output voltage or signal there. So as an inverting terminal, that the signal which comes here is going to get onto an inverting terminal. And the non-inverting terminal is the one which is going to be earthed. So the only signal which will be allowed to go through an operational amplifier will be inverted. And for that particular case, we'll be able to find that if we're going to look to a signal, the input signal, if we're just going to look at the input signal, if the input signal it is something like that, then the output signal, as long as it is inverted, the output signal will be inverted. And here you can be able to see it's moving like this. But an inverted signal, which is amplified, will be moving in an opposite direction. But it is inverted. So it's completely 180 degrees, the output signal, out of phase with respect to the input signal. And that is when the operational amplifier acts as an inverting amplifier. The output signal is really inverted to about 180 out of phase with respect to the input signal. So the output signal here will just be amplified, but it will be out of phase 180 degree with respect to the input signal. So this is the first case whenever I talk about an inverting amplifier. The second case is whenever an operational amplifier is used as a non-inverting amplifier. Whenever it's used as a non-inverting amplifier, then we are going to have the opposite of this, that our signal comes through a non-inverting amplifier. And actually the operational amplifier will be connected in this way. That the signal goes, our input signal goes through a non-inverting amplifier. But the inverting terminal is the one which is going to be earthed. So this one is going to be earthed. And the output signal will be obtained at that particular terminal, output terminal, as usual. So with this case, then with this we're having now a non-inverting amplifier. The signal which gets to an operational amplifier gets through a non-inverting terminal, and the output will be obtained through the output terminal with respect to the ground. And if we are just going to, if we are trying to compare now the input signal, if the input signal is something like this, now the output signal will not be inverted as for the first case, will now, because it is a non-inverting, so with respect to the time of course here, you'll be able to find that the output signal will be in phase with the input signal, will not be inverted. That is why we are saying this is a non-inverting amplifier. So the signal will be amplified, not as small as this with respect to an amplitude or whatever, but it will be amplified. So it will be as bigger as that one, but it is in phase with this one here. So that is for the non-inverting amplifier. So we are having such kind of a connection like that. So these are the two features how the operational amplifier can just be operate or can just be able to work. Okay, students, now let us look another features of an operational amplifier. Sometimes with the use of an operational amplifier, we could have what we call the negative feedback. That with our operational amplifier we are having here, we could have what we call the negative feedback. That our operational amplifier connected there, we could have an internal resistor there, for example, and our output terminal to be somewhere there. So sometimes if I'm taking, let's say, the input voltage is applied across there, for example, this is inverting and non-inverting. Sometimes we could have what we call a negative feedback. The negative feedback, some part of the output signal is brought back to an inverting terminal of the input signal. This is what we call a negative feedback. This particular signal, whenever it's brought back to the input inverting terminal, really it reduces the input signal. But it is done so for the purpose of making the operational amplifier to be more effective, just depending upon a designer. And this particular signal which is brought back actually should have to pass through a particular resistor, what we call a feedback resistor, RF. And this particular feedback signal passing through a feedback resistor will make the input signal to an inverting input terminal be reduced, and therefore to effect the actual output voltage. This is done, whenever this is done, actually it will be affecting the voltage gain of an operational amplifier. Now, just depending upon the design, this could just be very useful whenever a designer is just using a particular operational amplifier for a certain purpose used in an electrical circuit. Okay, so let us just look the uses of an operational amplifier. So there are several uses of an operational amplifier. First of all, an operational amplifier can be used as an inverting amplifier. Can as well be used as a non-inverting amplifier. A non-inverting amplifier with a negative feedback. Can as well be used as an inverting amplifier with a negative feedback. It can as well be used as a summing. It can as well be used as a summing amplifier. It can be used as a summing amplifier. It can be used as an integrator or differentiator. It can be used as integrator. And as a differentiator, it can be able to perform the integration and differentiation. It can as well be used as a comparator. It can be able to compare some voltages. It can as well be able to be used as to compare the voltages, or for the voltage as a voltage follower. Okay, it can be used as for these three parts. But we shall be able to, will not be able to go through all of these particular uses. But basically, we shall be able to try to touch some few parts where the operational amplifier can just be used. Okay, so let us just start. We shall be able to look one or two. Let us start by looking, let's say, an operational amplifier as a summing amplifier. A summing operational amplifier. Whenever an operational amplifier is used for an addition, summing up some input voltages, then we are having a connection to be looking like this. That we could have some various input voltages. We could have some various input voltages. For example, we could have so we can call this to be R1, R2, and this to be R3, and this to be connected. We could have the input voltage one here, and we could have another input voltage V2 here, and then we could have another input voltage V3 there. So that we are looking the addition of this particular three voltages, V1, V2, and V3, to the output terminal here, okay? Such that whenever we are having this kind of the circuitry, then it's whenever we are having an operational amplifier be used as a summing op-amp, summing operational amplifier. That with a voltage V1 goes like this. It means that we'll have a current here, I1, gets to that particular point, as well as the current I2 gets to that particular point, and the current I3 getting to that particular point, such that the total current I will be coming to this point. But as long as the input terminal here is very big, all of the current, all current will be getting out from this particular point. Let me call this to be point N, and let me call this point here to be point P. The point P is earthed. Remember, the whole of this particular amplifier is earthed. That is, it is 0 voltage. The ground, that is the earth, that is 0 voltage. Such that whenever we are taking this, if we are just going to use the Kirchhoff's law, the Kirchhoff's current law, let's say at a point N, then we are taking that the sum total of the current I1 plus I2 plus I3, the whole of this will be equal to the current I. And this current I actually will just be equal to the current that goes to the feedback resistor, RF. So for I1, we'll be talking about V1 over R1. For I2, this will be equal to V2 over R2. For I3, this will be equal to V3 over R3. And the whole of this will make the sum total of the current I, which actually will be equal to the current IF. The output, the current IF current goes to the feedback resistor, and this will depend upon the voltage at this point minus the voltage at that particular point. So this will just be equal to the voltage at Vn minus V out over RF. But remember, the voltage at point N is just equal to the voltage at point P, which is just equal to 0 because it is visual earth. So we're going to have V1 over R1 plus V2 over R2 plus V3 over R3. This is equal to minus V0 over RF. If I'm taking R1 to be equal to R2 to be equal to R3, let me take this to be equal to the input resistor I. Then it means what? It means that I'm going to have the V1 plus V2 plus V3. The whole of this will just be equal to minus Ri over Rf times V0. And therefore, you can just be able to find that if you transpose and put V0 to be the subject of the formula, actually we'll just be having V1 plus V2 plus V3 Rf over Ri. The V0 will just be equal to this much with the negative sign there, of course. Such that if we are going to take R1 to be equal to R2 to be equal to R3 to be equal to Ri, if we take this to be equal to Rf, then we are just going to get the whole concept of an additional. That is, the output voltage for that case will be equal to V1 plus V2 plus V3. Because Rf will just be equal to Ri, the input resistor, and the feedback resistor will just be the same. And eventually, we'll just be able to find that the output voltage is just equal to the sum total of the input voltage V1 plus V2 plus V3. But it is inverted. That's why we're having with the negative sign there. This is the first case whenever we are using our operational amplifier as a summing amplifier. Okay, now let's go and look at the second part of an operational amplifier, how it can be used. Well, let us go look at the way how an operational amplifier can be used as an integrator. An operational amplifier can as well be able to perform integration. And this process can just be achieved whenever an operational amplifier is being connected in this way. So we're going to have this to be our capacitor and this to be the resistor, the input resistor. The input resistor. Okay. Now, from the Kirchhoff's current law, we are going to look at the current right at that particular point. Let me call this to be point N and this to be point P. We all know that from the Kirchhoff's current law, the current which comes here, most of the current will just be going to the capacitor there. Why? Because the input resistance of the amplifier is really very big. So almost all of the current will be going to the capacitor, and therefore point N will just be at 0 voltage. So the potential at point N is the same as the potential at point P, which actually will just be equal to 0. Okay, so having obtained that, it means what? It means that from the Kirchhoff's law, that the current which goes to the point N is the same as the current which goes away from the point N. So it means that the input impedance to an operational amplifier goes to infinity. It's really very large. So all of the current I will just be equal to the whole of the current which goes to the capacitor there. So the current I will just be equal to the current that goes to the capacitor there. And from the Ohm's law, whenever I'm talking about the current I, then this is just be equal to the voltage over the resistance. But this current I will just be equal to the input current minus the voltage, the input voltage minus the voltage at point N over R, the input resistor R. And this will just be equal to the current which goes to the capacitor I. And this is just be equal to dq dt, okay? Because we all know that the current I is just be equal to dq dt. But you all know that the Q is just be equal to CV. And then we can just be able to proceed and see what we are going to obtain. Okay, so from this expression, as we already seen, we are taking the input voltage minus the voltage at N over R, the input resistor, to be equal to dQ dt. But the Q, the charge, is just equal to C times V, where C is the capacitance of a capacitor times V, the potential, depending upon the difference between the voltage at this point and the voltage to the output terminal. So that the whole of this expression will just be equal to time derivative of C times V. But the C is a constant, so you can take outside. So we shall be remaining with the time derivative of V. Now this V will just be equal to V at N minus the output voltage. So this will just be equal to this much. But remember, the Vn just be equal to Vp is equal to 0. So here we'll just be remaining with input voltage over R. Input voltage over R. And therefore, if we rearrange this particular expression, if we remember again, the Vn here is also 0. So actually, we'll be having input voltage over R to be equal to minus C, to be equal to minus C d V naught over dt. And if we write in a very good way, then we shall be able to find that input voltage over RC to be equal to minus dV naught over dt. Actually, our interest is to obtain the output voltage V naught. So the output voltage V naught will only be obtained after rearranging this expression and doing an integration. So that we'll just be able to find that the V naught there will just be equal to 1 over RC with the negative sign there. But you'll have just to integrate that if I'm taking dt, the V naught there will be equal to VI dt. Input voltage there times dt. So this will just be our final expression, which shows us the output voltage V naught there is inverted because of the negative sign which appears there. And eventually you can be able to compute and be able to obtain the output voltage. So you can be able to see so straight that this operation amplifier can as well be used as an integrator in this way. Whenever you are connecting a capacitor in place of the feedback resistor, we are connecting a capacitor there, and the whole configuration of the circuitry of an operation amplifier is as shown there. Okay, so students, let's go to the question number 1. And this question number 1 takes us to an example. We have just looked at an operation amplifier as a summing operation amplifier. So the question goes like this. Study the below summing operation amplifier designed by a student, whereby R1 is 1.5 kilo ohm, R2 is 3 kilo ohm, R3 is 1 kilo ohm, and the feedback resistor is 15 kilo ohm, and the V1 is 4 millivolts, V2 is 2 millivolts. Now, if the output voltage has been planned to be 2.7 times 10 to the power negative 2 volts, then you determine the input voltage, which is V3. So the input voltage from the circuitry, we are having the input voltage, we are looking now the voltage V3 here. Okay, so all other values, the V1, V2, and the V3 are given, and we need now just to look all about that. So that is where our question is, and we can just be able to solve this very quickly with whatever we have just looked previously. So we are having our operation amplifier. Okay, so we are having our operation amplifier, as I've shown it to you, just like this. The values for R1, R2, and R3 are given, and the voltage V1 and V2 are also provided. We are asked to look what is V3, the input voltage is V3, because the output voltage is also given, and the feedback resistor there is also given. Now, as we have already seen previously, that the potential at this particular point N and the potential, let's say, at this particular point P, it is the visual F, and that's just equal to is almost equivalently to a 0 voltage, or just like SD. So that the total current which goes through that resistor will sum up to the total current I. And the current I which goes to the input part of the operation amplifier, because of the high impedance to the input side of the operation amplifier, most of the current will go to the feedback resistor. So this is IF. And therefore, we could just be able to find that the current I1 plus the current I2 plus the current I3, this is equal to the current I. And this current I actually will just be equal to the current which goes to the feedback resistor. But the current I1 is just equal to V1 over R1. The current I2 is just equal to V2 over R2. The current I3 is just equal to V3 over R3. So this is just equal to the current IF. The current IF is just equal to, if we can be able to substitute for those particular values. That is, what is the V1? The V1 is given there, which is 4 millivolts. So V1 is 4 millivolts, so we can be able to take 4 millivolts and over R1. The R1 there is just equal to 1.5 kilo ohm, 1.5 times 10 to the power 3 kilo ohm, plus the V2. The V2 is 2 millivolts, that is 2 times 10 to the power minus 3 volts, over R2. The R2 is 3 kilo ohm, so the 3 times 10 to the power 3, plus V3. The current I3 is V3. The V3 is the one we are looking for. So over R3, the R3 is 1 kilo ohm. That is 1 times 10 to the power 3. So the whole of this is just equal to Vn minus V0. The Vn is 0, so we'll be having minus V0 over Rf. The output voltage, is 2.7. 2.7 10 to the power negative 2 volts over feedback resistor Rf. The Rf there is 15 kilo ohm. That is 15 times 10 to the power 3 ohms. So then we can just be able to compute here to determine what is the V3. Okay, so you can be able to see that these particular values can just be cancelled, and we could just be able to take 4 10 to the power negative 3 over 1.5. This can just be computed, and we can be able to obtain this very quickly. If you can be able to use your calculator, you'll be getting 2.667 10 to the power negative 3, and if you add it 2, then you'll be getting 6.67 10 to the power negative 4, and you add it plus V3. So the whole of this will be equal to 2.7 10 to the power negative 2. We'll be getting 1.8 10 to the power negative 3. So our interest is to determine what is the V3. So if we add up here, if we're just going to add up here, then you are having something like, this is 3.33337 10 to the power negative 3 plus V3 is equal to 1.8 10 to the power negative 3. So the V3 will be equal to this much minus that much. So we are taking, remember here there is a negative sign, so the negative sign is there. So we are taking this minus this much. So we'll be taking 1.8 10 to the power negative 3 minus 1.8 10 to the power negative 3 minus 3.337 times 10 to the power negative 3. So we'll be having minus 5.1337 times 10 to the power negative 3 volts. The input voltage at this particular terminal will be supposed to be this much. Will be supposed to be this much to make the output voltage be equal to 2.7 times 10 to the power negative 2 volts. So this will be the value for the voltage V3. Okay, students, let's go now to the question number 2. The question number 2 takes us to a case whereby an operational amplifier is used as an integrator. So the question goes like this. Given the below circuit diagram of an operational amplifier as an integrator, having a capacitor of 5 microfarad and an input resistor of 1.8 mega ohm. Now, if the input voltage Vi suddenly changes from 0 volts to 1.5 volts, now what will then be the output voltage V0? So we're having a circuit just like this, and we could just be able to use this source trait to solve from the values which are just given there, okay? From the operational amplifier we are having, there, so the input signal is there. And we could just be able to find that, as already said, that the current, the net current which goes to this particular point N, almost all of the current will be going to the capacitor there. So that particular current I actually will just be the current which goes to the capacitor. And this current I will be depending upon the voltage between this point and that particular point, the input voltage. So that you will just be able to find that this will just be equal to the input voltage, the current which goes to this particular point from the Ohm's law, which is just equal to IR. At that particular point will just be equal to the input voltage over that particular resistance R. And the whole of this actually will just be equal to the current which goes to the capacitor. And the current which goes to the capacitor, as we have seen, will just be equal to dq. This will just be equal to dq dt. But the q there is just be equal to CV. And what we have just done previously, it takes us all of the way to obtain the output voltage V0, such that the output voltage V0 we obtained to be equal to 1 over RC, the integral of the input voltage dt. And using this particular expression, then we can just be able to calculate, and we can just be able, it's just a matter of substitution of what is R, the input resistor, what is C, the value of the capacitor there, and having known the input voltage V, we can as well just be able to calculate and be able to know whenever a current suddenly changes from 0 to 1.5 volts, what will just be the output voltage V0. So if we are just going to substitute those particular values, then we can just be able to find the answer. Let us just look that the V0 here is just equal to 1 over RC. The resistor R is 1.5 mega ohm. That is 1.8, sorry, mega, okay? That is 1.8 10 power 6 ohm times C is 4 microfarad. So we multiply 4 times 10 power minus 6, and then the whole of this, we just have, we all know what is the VI, the input voltage, which changes suddenly from 0 to 1.5 volts. That is the input voltage, that's 0 to 1.5 volts. So we just, it's a matter of just multiplying to 1.5 volts, from 0 to 1.5 volts. Now, if you compute for that particular expression with respect to t, so that if you compute for that much, you'll be able to obtain, you obtain 0.228 volts. And remember, this is the negative sign, so it will be having a negative sign there. It shows that within such a very small time, changing the voltage from 0 to 1.5 volts, the output voltage will be equal to this much, changing in terms with respect to the time t, such a very small time. So the voltage will just be like of that particular magnitude, but it is really inverted with the negative sign, negative 0.208. with respect to the time t. So this will just be our output voltage. And you can just be able to see that's the way how an operational amplifier can just be used as an integrator. Okay, students, then having seen the two examples, then we can see one question for you as a homework, and that I'll just be able to give you just some hints. Okay, students, now let us go and look our question here. The question goes like this. The operational amplifier circuit below has been designed by students to be a summing amplifier with two inputs voltages, V1 and V2, across R1 and R2 respectively. Given that R1 is 12 kilo ohm, R2 is 8 kilo ohm, and the feedback resistor RF is 45 kilo ohm. Determine the output voltage when V1 is 0.85 volts and V2 is 0.54 volts. Our circuitry is just like this. So we are having some two input voltage, V1 and V2, across R1 and R2. So we are given the value for the feedback resistor, and we are being asked to determine the output voltage V0 there. So that is the question we are having, and you could just be able to find that having given that particular question, you just have to use that particular formula we had just applied for the first case. Whenever we are taking our operational amplifier as a summing amplifier. So we are having our circuit to be like this. So we are given the R1 is 12 kilo ohm. This one R1 is 12 kilo ohm, and R2 is 8 kilo ohm. And the feedback resistor RF there is given to be 45 kilo ohm. And we are asked to determine the output voltage. Okay, if V1 is 0.85 volts and V2 is 0.54 volts. So what you are supposed to understand is that the actual current which goes to this particular point, actually due to the high impedance to the input terminal of the operational amplifier, will make almost all the whole current to be going to the feedback resistor, such that the current across R1, which is I1, plus the current across R2, which is I2, the whole of this will just be equal to the total current I, which actually is equal to the current that goes to the feedback resistor. And the current I is just equal to V1 over R1. The current I2 is just equal to V2 over R2. And the whole of this will be equal to the current that goes to the feedback resistor, which will depend upon the difference of the voltage at this particular point N minus the output voltage over the resistance of the feedback resistor. But this much is just equal to a 0. So you can be able to substitute for V1, V2, R1 and R2 to obtain what is V0, as long as the feedback resistor RF is known. So it's a matter of just a substitution, and I hope you can just be able to do this whenever we are taking our operational amplifier as a summing amplifier, and so that eventually you will be able to obtain the output voltage V0 to be equal to the sum total of the first voltage V1 plus the voltage V2. So this so by a computation you can be able to compute and be able to obtain the actual final answer, but you will just be able to get this arithmetically once you just substitute for the V1, V2, R1 and R2, and you know what is the RF, then you can be able to know what is the V0. That will just be the question for you as a homework. I'll just leave it for you to go and do it at home, and I hope you can be able to do it comfortably. Okay, students, having gone through these particular questions as well as this question for your homework, then I believe you can just be able to do a lot of questions with regard to an operational amplifier. There are several applications, as I've already said that, but it's not easy for all of them to take some examples right now here for you. But I believe you can as well be able to go and try to do it on your own. And having known all of the basic properties, all of the basic expressions of the treatment of an operational amplifier, I believe you can just be able to do those questions comfortably. Okay, thank you students, and see you next time.